So what is next? Well, I have found something for a policy pi, then what should I do?
Control.
Right? I should do the control case. So how would you do this for control, right? Come on, somebody say something before I say done.
Q learning.
Yeah, use the Q values, we already know. Do use LSTDQ and then do policy iteration. Right? Take a policy, solve it, find the Q function, be greedy with respect to that, get a new policy, evaluate that, and so on and so forth. Okay, what's the tricky part here? Right, so this is what we are saying. So for every state, I mean, where the argmax is done state wise, right? If this is little confusing, then right. So now what is this? I mean, this is the easiest for me. Okay. Right, or more appropriately theta hat phi t. Okay. Now what are the problems? This is we have gotten till here. So what are the problems here?
The argmax.
Huh?
The argmax is over one thing.
Sorry?
Argmax is over one action.
Argmax is over.
One action.
So we always, whenever we do policy iteration, we always look at deterministic optimal policy, right? So it's okay. One action is fine. Now what is the problem? Well, it all depends on how my states and actions are represented, right? So I am looking at a maximization problem. If my A dimension is simple, it is fine, but if my phi SA parameterization somehow translates that into a continuous value, right? Or if my action itself is a continuous valued action, right? How will I do this? Right? If my state is a continuous valued state, what do I mean by saying I am going to find the max on every state? Right? My state might be continuous valued, but my phi S might be something smaller, right? Something more compact, right? So if my phi SA happens to be really spanning RK, right? So what does it even mean to say I am running a maximization over that representation, right? So we will have to come up with some clever way of doing this, right? There are many ways in which people have set this up as a linear program, and people have set this up as other ways of solving this, right? There are clever tricks which people come up with, and there are many ways in which you can solve this, right? So one thing which I particularly liked, okay, this is from the old technique from like 2003 or something. So what people do is they somehow solve this for a few states. They solve this maximization problem for a few states, and then what they do is they get an estimate of the pi hat by solving a classification problem. So what will I do is I will solve this for some number of states, right? Some number, right? So yes, give me some number. Some S1 to SQ, right? So it's a bad thing to use here. I used all letters. What letters haven't I used? Huh?
SX.
Yeah, so S1 to Sj, right. So I have solved it for some problems S1 to Sj, and what do I have? I have corresponding actions A1 to Aj. What this is? This is yes, this is pi s, right, pi t plus 1. I pick some arbitrary specific points in state space, right. It can be a continuous state, right, it can be continuous actions. With continuous action I have some way of maximizing this. So I just pick some points in space and I solve this. So now what I do is give this as a training data, not this. By this I mean I will give phi 1 of S1 to phi k of S1 comma yeah, I give this as a training data to a classifier, right, and have it solve the problem, learn a classification problem. Right, why a classifier? I mean, because A1 to Aj are some fixed set. If it is a finite action case, right, if it is a finite action case I will give it to a classifier. If it is a continuous actions case I will give it to a regressor, right, that will give me some value that will generalize across all the unseen states. What's that?
Policy, like we are doing the same thing, the policy that we are doing, the value function.
Yeah, we are representing the policy using an approximator. Right now we do not have an explicit representation for the policy, right, we are just using the Q function as a representation for the policy. So we are saying if you want to recover the policy you just be greedy with respect to the Q function, right. But this, since this is a hard problem to solve, right, I am trying to approximate it by saying okay, instead of solving this exactly, this maximization explicitly and getting a pi representation, I am going to represent pi using some kind of a function approximator, and now I still have a way of generating these samples if I want, right. Yes, no, people see that? See, once I have a policy, I can start from state S, go to this policy, pick out whatever is my action A according to this policy, perform that, hit the next state, the next action. What I am doing here? So this is the problem that I really want to solve, right. Suppose my S is a continuous state space, right, then it becomes hard for me to solve this and get a closed form expression, or I will have to solve this maximization every time I come to this state S, I will have to solve a maximization problem and find what my action A is, right. I do not want to do that, I want to say pre-compute it and keep it as an explicit policy, so that I do not have to do the maximization every time I have to pick an action. Right now we just do the maximization every time we pick an action because it is easy to compute, because we have a lookup table, it is easy to compute. But if I have to solve a linear program every time I have to find the action, I do not want to do that, I want to pre-compute this, right, and I do not want to solve it for every state. What I do is I sample say j states and I solve the maximization problem on those j states, right. I find the best action for those j states, so I have A1 to Aj, right. Now what I do is I create a training data that says okay, the input is phi 1 S1 to phi k sk, phi k S1, and then the output is A1. So like this I form a training data, right, where the desired output is the action that came out of the maximization, and the input to that is the encoding of the state, some encoding of the state, right. So now this will learn some function f, right. So next time I come to a state, I pass the state to the function f, okay, and it is going to spit out a action, and I will take that action. So the f is my representation for the policy pi. It is another approximation. So I am just maintaining an approximate representation for the policy also. So that is one way of handling this, right. And of course it has its own thing, the phi need not be the same as this phi, it is a completely different function approximator, right. So I can use a different phi if I want, right. And first of all, if I am doing Q functions, this phi will be a function of S comma A, right, and that is a function of states. So I have to use a different set of features anyway, right? And this is just one trick for doing this, right. And yeah, so what do you think this kind of an approach is called? Policy iteration, least squares policy iteration. It means policy iteration, no, it's least squares policy iteration, right. So, can we put up the LSPI JMLR paper also online? Right. So, I took the discussion for LSTD and LSPI from the same LSPI paper. So, if you read the original LSTD paper, it's a little hard to follow what they are doing, because it was like a 7-page paper or 8-page paper, short paper, and there is a much more expanded discussion here, and they use the uniform notation for both LSTD and LSPI, so it is easy to follow. Okay. And then they have a whole bunch of experiments. There are small things that you have to be careful about, which they describe very nicely in the paper. Okay. So, that is one thing. The next thing which I wanted to talk about was something called fitted Q iteration. It is very similar in spirit, right, very similar in spirit. So, what you do there is you do Q learning, right. So, how do you do Q learning? You start off with a fixed set of samples, right. You start off with a fixed set of samples, then you generate your targets, right. So, how are the targets generated? Like, so like we talked about here, right. So, I am going to generate a V pi as my target, right. But that V pi is not the target. So, what will be my target in Q learning? R plus max over next, right. So, I generate those targets, right. So, what do I do is with the same data, right, I train a function approximator to approximate that target. Okay. Sounds very similar, right. I train a function approximator to approximate the target, then what do I do? Now, one thing here is I did not put any linear constraints or anything here, right. I can take any function approximator, right, that will approximate this Q function. Then I will take that approximated Q function and create a new training data. Why? Because my training data depended on the Q function's output, right. I am seeing too many blank spaces. So, I have some Q hat to begin with, right. So, my training data will be so phi si, remember that phi si is a vector, right. So, that is the encoding for the state, right, or encoding for the state action pair. Okay. So, I give that as the input, and the output is Ri plus gamma max over A Q naught hat Si prime comma A, right. So, like this I will do this for all I. So, the data is of this form. Okay. The data is of this form, I form the training data of this form, right. I feed it to my function approximator. So, whatever is my function approximator, right. So, my function approximator will take this as the input, okay. From here I create this, then it is going to give me back Q1 hat, right. So, I am going to take Q1 hat, I will create that. Okay. That makes sense, and solve that, give me Q2 hat. Right, and I keep going. So, what are the things you have to be careful about here? Well, whether I can do this maximization properly, that means I should have tried all actions from here, right, for me to be able to do this maximization. So, I need to have generated sufficiently random samples, right. If I have not generated sufficient number of samples, right, then this is going to become a little tricky. Right. So, these are some caveats with the fitted Q iteration.
Generate that data from that Q. So how are you generating that Ri from that Q function?
So, my data is of this form, right? My SI, AI, Ri, SI dash is the training data I have. This is the trajectory that I have written. From these trajectories, I am generating that for my but that for my regressor. Right. So, my regression problem has to be something like this, right? So, this is the where we start. I erased it unfortunately, but that is where we started off with for the whole thing, right? And from there I said we are going to do a least squares fit, and then we assumed linear parameterization, and then we derived all of this, right? So, here we are not saying, we are not restricting ourselves to least squares. You could do least squares with a linear function approximator, but what we are trying to do is the iterative part here, right? So, I am trying to converge to the optimal Q function without going through the policy iteration cycle. This is more like getting inspired by Q learning kind of an approach. This is called fitted Q iteration. So, it is iterating over the Q function and I am fitting a function to it. So, it is called fitted Q iteration, and I do not know. So, I might actually come back to fitted Q iteration and tell you a little bit about some of the nice properties and caveats on fitted Q iteration, because it turns out that if you have a fixed set of samples, right, and you have really no way of generating more samples, right. So, empirically fitted Q iteration seems to do pretty well. Okay, that is one part of it. The second thing, there are a lot of things on in the fitted Q iteration setting that people are now reusing in deep Q learning, right. In the deep learning, all this if it does not ring a bell, Atari, AlphaGo kind of stuff, right. A lot of the ideas that were developed in this fitted Q iteration setting is being reused, right. So, I would really like to come back and cover that a little bit, maybe next class or maybe later, right.